Okay, so before starting with complex variables, we need to actually understand some of the basic things. And for that purpose, what I will do is I'll just take some small, what you can say, things from the stuff that you have studied in your previous classes. Because in this chapter, your basics will be a lot useful than what we will learn here. Okay, so the basics are complex number is denoted by Z and it is of the form. Yes, can anyone tell me what does a complex number look like? X plus I y. Okay, so any complex numbers are usually denoted by Z and it is of the form x plus iy where x is the real part and y is the imaginary part. Okay, so every complex number can be represented on a graph, whereas the x-axis is the real parts are plotted on the x-axis and the imaginary part is plotted on y-axis. So this is also called the imaginary axis. Imaginary axis is y-axis. So every complex number x plus iy can be plotted here. Say if I have 1 plus I, so this 1 will be the real part and this I whose coefficient is 1 becomes the imaginary part. So the point on this plane would be 1 comma 1, which is also 1 plus I. So this is how we plot uh, every complex number on the complex plane. So whatever things that we study for real numbers like derivatives, integrations, all those things can be brought up to in complex also. So just like you define a function f of x in the real numbers where x is a real variable, it takes values uh, from the real numbers. Similarly, I can define a function f of z where z is a complex number. Okay, and once it is a complex number, for this complex valued function f of z, what I can do is I can define derivatives, I can define integrations, I can define series, and everything that we have done in the real number can be extended to the complex number. Okay, so whenever I say a complex variable, it means that it is z, and that z is of the form plus iy. Okay, after this, there are some basic properties of the complex numbers, like what is mod z? Yes, anyone? Can you tell me if you remember what is mod z? Mod z is nothing but under root. If you don't know, please note it down. Under root x square plus y square. What does this graphically represent? Graphically, this represents the length of the vector from origin. If you are treating it as a vector, or if I just want to talk in terms of scalar, then I will say is the distance from origin to z. So distance from origin to the point x comma y. X comma y, I also mean to say x plus iy. Okay, so mod z formula you will have to remember in many of the examples you will encounter this. For every complex number, this is also denoted by R. So R is said to be the modulus of Z. Modulus. Okay. Then for every complex number, I can also define theta. Theta in general is given by tan inverse of y by x. Of course, we have to take the quadrants in picture, but this is the general formula. Tan inverse of y by x. This is called the argument. Argument of z. Now, there are different ways of representing a single complex number z. So, this complex number can be written as x plus iy. This can also be written as r in bracket cos theta plus I sin theta. This can also be written as r e to the power I theta. This is called the polar form. This is called the Euler's form. These are not I mean, different from each other. These are just different types of representations for a single complex number. And you can see that r and theta plays a major role over here, as r and theta are required to represent a complex number in polar form as well as the Euler form. Another thing that I really want to recall is the conjugate of a complex number. What do we mean by conjugate of a complex number? Let z is equal to x plus iy be the complex number, then conjugate of z, conjugate of z equal to x plus iy is denoted by z bar and is defined as z bar is equal to x minus iy. Read the definition very carefully. Again, this is conjugate is something that you will encounter a lot of times in different properties. And after you understand it, tell me what is the conjugate of 2 plus 3i. Yes, but where is Samarjit? Chandratej?
हाँ यस सर
Where are the other students? Samarjit का है.
तो ग्रुप पे तो डाला था मैसेज सबको ज्वाइन होने के लिए
Lecture खत्म हो गया. Previous one, whichever was going on.
यस सर यस
Okay. Yes. Can you tell me what is the conjugate of this 2 plus 3i?
सर 2 minus 3i.
So conjugate is 2 minus 3i. So what we generally do is, when I am finding out the conjugate of a complex number, we just change the sign of the imaginary part. That's what we do. Okay, so second example, if z is equal to I, then z bar will become minus I. Okay, this is how you compute the conjugate. So what is the use of the conjugates? Conjugates are identified in lot of properties, and one of the property that we will require from time to time is mod of z square is nothing but z into z bar. So when you take the product of complex number and its conjugate, what we get is mod of z square. Another z plus z bar. Yes, can someone tell me what you get when you take z plus z bar? Let's do the calculations over here. Z is equal to x plus iy. Z bar is equal to x minus I. So when you add two of these, z plus z bar, so what do we get? 2x. What is x? X is nothing but the real part of z. So z plus z bar is 2 times the real part of z. Similarly, I can do z minus z bar, which is nothing but 2 times imaginary part of z. Okay. Now, this much previous knowledge is, I think, sufficient. Sorry, necessary. For sufficiency, you will have to study more complex numbers. But let's go ahead now. As next thing we need to see is what is the complex valued function. A very important definition. I should start it.
So just a minute, sir. Z plus Z bar is equals to 2 times the real part of the Z.
Yes.
And the minus will stand for imaginary part. Okay.
Yes. Next, complex function. From this point, our actual syllabus starts. So, what we need to first of all understand what are complex functions. So I'll write down the definition. If by rule we can find one or more complex numbers, complex numbers W for every Z in bracket, the Z looks like x plus iy in a given domain. In given domain in C. Look, this capital C with a vertical line. This kind of C represents the set of all complex numbers. Okay, we say that W. We say that W is a function of Z and is denoted by and is denoted by W is equal to f of Z. Let's try to understand what this is explaining or telling us. So what I'm doing is I'm defining a function from a set D to the set of complex numbers. Okay, and D of course is a subset of the set of complex numbers. So it is actually uh, a function from, can also give this from C to C. So the functions those are defined, they take intake is done from the set of complex number and output to you get in the set of complex numbers. So what happens is if I give this function an input as a complex number, it will give me output as a complex number. So for example, what I'm defining is f of z is equal to say z square. I have defined a function. Okay. So for an example, I've defined f of z is equal to z square, and my question is what is f of I? Yes, who can tell me what will be the answer for this? F of I will be I square. What is I square? The value of I कैसा दिखता है? It is actually under root of -1. So I square will become -1. So f of I is equal to -1. Also, I can find out f of say 1 plus I. What will be f of 1 plus I? F of z is z square. So f of 1 plus I will become 1 plus I square. So 1 plus I into 1 plus I. The multiplication in complex number is actually same like you multiply the two brackets. So 1 into 1 plus I plus I plus I square. Uh, I can also use the formula, but I am going because you are new to this topic and should understand this very carefully. So I square is -1, so 1 and I square will get cancelled out, and the answer is 2I. So this type of functions are called complex functions. Now, here in this example, particularly, yes, Chandratej.
No, sir, sorry.
So, in this particular example, I talked about particular complex numbers. Okay, so the rule is given to you f of z is equal to z square, and I found out what will be the answer for f of I. So, by this rule z square, for a given complex number, I am getting another complex number. So, this is a complex function. And this type of functions I can write, uh, I mean, various functions can be given which will assign another complex number to the given complex number. So the first example is this. Second example, I can also define f of z is equal to e raised to z. Third, I can define as f of z is equal to sine z. Fourth one, I can also define as f of z is equal to uh, z into z bar, or a mod of z square. Let's take mod of z square. Okay. So what I'm doing in each of the cases is I'm starting with a complex number. I'm giving input as a complex number. I'm getting output as a uh, some complex number. Now, what is common in this? Uh, the common thing is, and this will be required, this technique will be required to solve all the differentiability problems and integration problems. A lot of things can be done using this technique. So I'll put z as x plus iy. So on the right hand side, I will get x plus iy square. So I'm working with the first function f of z is equal to z square. So f of x plus iy will become x plus iy square. Let's make the square a plus b square, which is a square plus 2 times ab plus b square. So what do we get here? X square plus 2xy I plus I square is minus 1. So this will become minus of y square. So what have we got? X square minus y square plus I in bracket 2xy. So I will sum up here and I will write this in a big rectangle. So what I have got, f of z is equal to x square minus y square plus I into 2xy. So my question is, a real part of f of z is equal to, what is it?
X square minus y square.
X square minus y square. So I will denote this by u of xy, and imaginary part of f of z is equal to, that is 2xy, which is v of xy. So what I'm trying to convey here is, you start with any complex functions, and f of z I can always write as u of xy plus I times v of xy. So when I say a complex function, I'm actually working with these two functions, the real part u of xy and v of xy. So every time I start with a complex function, I will always get two different functions u and v. So that is the point I want to make here. So as I have done for the first one, I can also do it for the second one. So I'll start with the second function and I will see what is the real part that I get and what is the imaginary part that I get. So look, even for objective examples, you should be able to do this for every function. Okay. So I'll start with the second function now. F of z is equal to e raised to z, and see what I get. So f of x plus iy is equal to e raised to x plus iy. So there is addition. So I can write this as e raised to x into e raised to iy by properties of indices. E raised to iy can be written as cos y plus I sin y. This is by Euler's theorem. What does the Euler's theorem say? Euler's theorem says that, again I'm writing it here, e raised to I theta, you can write it as cos theta plus I sin theta. This is given by Euler, and this is the property that I have used here. So e raised to iy I can write as cos y plus I sin y. So this will become e raised to x cos y plus I times e raised to x sin y. So what have we got? This is my u of xy. This is my v of xy. Okay. So this is a very important property. Yes, so
So
that
the screen keeps fluctuating between black and white, sir.
I think it's only for you. And why are you late today? You have missed almost all the important part.
Yes, sir. I had some network issues as well. Sir, I'll review the recording later.
Okay. I'll stop the sharing and share it once again. Let's see if there is some change. Clear? Is the screen fluctuating, Samarjit?
No sir, not yet. It's clear sir.
सर तुम्ही टाईप करता ना तेव्हा फ्लक्च्युएट होते ती.
अच्छा.
सर तुम्ही कॅनव्हास टर्मिनल चेंज करून बघा ना एकदा जर पॉसिबल. कोणता अजून
काय?
वाईट
कॅनव्हा?
सर कॅनव्हास टर्मिनल चेंज करून बघा ना. अजून कुठला व्हाईट बोर्ड असेल तर तो यूज करून
नाही ना,
बघा.
ऍक्च्युली प्रॉब्लेम असा आहे, दुसरा व्हाईट बोर्ड नाहीये, नाही तर मी कॅनव्हास यूजच नसतो केलं.
ओके सर. आता फ्लक्च्युएट नाही होत तसं.
Okay. So we will make a note of that thing now, as we have observed this in two of the examples, and as I said, it is a very important thing, and so we will note it down. And the note is W is equal to f of z can be put in the form W is equal to u of xy plus I times v of xy. For z is equal to x plus iy. So for every z is equal to x plus iy, I can write this w in the form u of xy plus I times v of xy. Okay, a very important point. This will help us find whether the function is differentiable or not. So our task here is, the next task is, I want to understand when a given function is differentiable, when a given complex function is not differentiable, if it is differentiable, at what points it is differentiable. So all these things I have to understand, and for that we will use Cauchy-Riemann equations. Okay, Cauchy-Riemann equations will deal with this u of xy and v of xy. So before we get to that Cauchy-Riemann equation, let's understand the differentiability here. There is this definition that you have studied in your diploma, and the basic definition for the derivative is, can anyone tell me what was f of x given, f dash of x given by f dash of a, I should say. Derivative of a function f of x at a is given by first principle. I just want to know the first principle. If anyone remembers, what is the first principle? And so the definition was a limit h tends to 0 f of a plus h minus f of a divided by, okay. So this was the basic definition of the derivative at a point A. So what does this represent? This represents derivative of f of x at the point x is equal to a. So this was for the this function that we were studying there was a real function. Okay, so it took values from the set of real numbers. It gave the answer which was a real number, and that's why this much was enough. But now I want to make a similar definition for the set of complex numbers. So if I want to study the derivative of a function f of z at the point z is equal to z naught. Okay, then. So there was one more condition. This limit should exist. Okay, if this limit exists, then we say said that the function f of x is differentiable at x is equal to a. And so in the similar manner, now we'll define for the complex numbers. So let w is equal to f of z be a unique single valued function of z defined in the domain capital D. Then w is equal to f of z is differentiable is differentiable at any point z is equal to z naught. Any point z if limit delta z tends to 0, capital F of z plus delta z minus f of z upon delta z exist. So if this limit exists, then I will say that the function is differentiable. And just existing is not enough. That limit should be unique along any path. And what do we mean by along any path? Okay, we'll understand it later while solving example. What do I mean by path? Okay, so in short, that limit should exist. That's all I want to convey. So when you are asked that whether a given a function f of z is differentiable or not at a point z naught, so what you should do is actually f of z plus delta z minus f of z upon delta z, limit delta z tends to 0. If this limit exists, you get a some finite value there, and it doesn't depend on any of the variable, then you can declare that yes, the function is differentiable. There is another way of writing this first principle, and the way is limit z tends to z naught f of z minus f of z naught upon z minus z naught. Even this limit can be used. In some of the examples, this may be used and give you the answer very easily. So this checks the differentiability at z is equal to z naught. At z is equal to z naught. Okay. So whichever definition is comfortable with you, or whichever definition is good with the given example, you can work with it. Fine. So as we have understood the definition, we will quickly study some of the examples where I can check whether a given function is differentiable or not. So find whether the following functions are differentiable. An example, find whether the functions, the following functions are differentiable. Differentiable. First one, f of z is equal to z cube at z is equal to I. So what I want to check, I want to check whether the function f of z is equal to z cube is differentiable at z is equal to I. So this is my z naught, okay? And at this point z naught, I need to check whether the function is differentiable. So what I will do is f dash of z naught. What is the definition? Limit z tends to z naught f of z minus f of z naught upon z minus z naught. So I will check whether this limit exists or not. So this is limit z tends to, what is our z naught? At what point you are checking the derivative? At I. Z tends to I. What is your f of z? F of z is z cube minus, what is f of z naught? I raised to 3 upon z minus I. So now what I can see, limit z tends to I, you directly put I at the place of z. Of course, mathematically speaking, that shouldn't be the case, as the value of z is approaching I. Okay, so I will emphasize on what I meant by I. So can anyone tell me where is this point I on this complex plane? Yes, anyone? Where is the point I on this complex plane? So are you able to plot this point I on the complex plane? This is your real axis. This is your imaginary axis. On y-axis, there is this point I. So this will be 1 and this is actually I. Okay. Now z tends to I. What do we mean by, what is the definition of a limit? Okay. What do we mean by limit z tends to I is, so I will write down the statement here. Z tends to I means z is approaching I. Okay. So if this is the point I on my complex plane, by how many paths can a point reach this I? So how many paths you can draw that will lead any complex number to I? 1, 2, how many paths you can draw? How many ways you can reach I? That's my question. So assume that you are some point on the complex plane and you want to reach I, and how many ways you can reach there? 1, 2. Yes, Samarjit, how many ways do you have? So you can come to I from this side through y-axis, yes or no?
Yes, sir.
You can come to this I from this side also. Then if I have a parabolic path, I can also reach to this I through this side. From this side, there can be a parabola passing through this, so Z can reach from here to. So there are infinitely many paths by which a point can reach I, a parallel line which is parallel to the x-axis. So reaching to this point I can be done from any side. There are infinitely many paths through which you can reach this I. And if this is very difficult to understand, I'll just consider a real line. This you may have done in your diploma classes, and this is 0, and you were studying x tends to 0. So you saw that x tends to 0 plus, x tends to 0 minus. This is what you have seen in your diploma. So if I want to reach 0 on a real line, there are only two ways. Either I can reach 0 from this side, or I can reach 0 from this side. But in complex plane, it is not the case. Okay, so there it was just a straight line. So it was like a railway track. So if you want to reach a platform by a track, you can either come from one end, or you can come from the other end. There is no other way. Okay, but when I am in a complex plane, there are different paths through which I can reach this eye. Okay, and that's why while talking about the differentiability, I mentioned that the limit must exist along all the paths. Okay, so anyways, if you didn't understood it well enough, still we are going to look for other examples where we will have to talk about the different paths. Now, let's come back to this. You can see that as z tends to I, the value of z will become I, and you get 0 by 0 form. Once you have 0 by 0 form, what we do is we use Lopital rule. So what does the Lopital rule says? If after substituting directly this I in the equation, I get 0 by 0. In that case, what you have to do is you take the derivative of numerator, limit z tends to I, and take the derivative of denominator. So derivative of numerator is 3 z square upon derivative of denominator is 1. Now put I in the place of z, and you don't get 0 by 0. So that is 3 times I square, and the answer is minus 3. So limit exists and it is unique, so the function is differentiable. Function is differentiable. At z equal to I. If you have any problem, you can ask.
Sir, as you told that we will take the derivative of z cube and the denominator z. So then what with I?
Derivative of I is 0, na? I is a constant.
Okay, and minus yes.
Do you know what is L'Hopital rule? First of all, let me just
No,
confirm
sir.
this. Okay, so I'll mention it over here. It is a very famous shortcut method to determine the limits. And what it says is a limit if we have 0 by 0 form for limit x tends to a f of x upon g of x, then limit x tends to a f of x upon g of x will be equal to limit x tends to a f dash of x upon g dash of x. I don't actually remember the exact statement, but I have tried to frame it in different words. If you Google it, you will find it somewhere. But meaning won't be different. Whatever I have said, the meaning will be the same, whatever statement you get in that. So the L'Hopital rule says that I want to find limit x tends to a f of x upon g of x. Okay, and what I will do is I will directly place a in the numerator and denominator. Say for an example here, as you can see, I have directly placed I in terms of at the place of z. So I'll get I cube minus I cube numerator, I've got 0. Similarly, I have placed I in the place of z, I minus I have got 0. So
Please,
0
sir,
by
can you repeat, sir? Sir, sorry, sir. Can you please repeat, sir? From the big, sir, either say limit z tends to I say.
So I have directly placed I in the place of z. So I cube minus I cube, what you get is 0. If you place I at the place of z in denominator, so again you get 0. So this value will be 0 upon 0 form. So L'Hopital rule says that whenever you get 0 by 0 form, that limit will actually be equal to the derivative of numerator upon derivative of denominator. So that's why what I did is I have took the derivative of this thing, just 3z square, derivative of the denominator, and then I have put the limit. Now I can place I in the place of z, and I'm getting a non-zero term. Okay, so that is how you use the L'Hopital rule. Fine, if you want, you can write down the L'Hopital rule, or I will go ahead.
Yes, sir, just a minute.
In case if some variable was associated with I, then sir, we can't use this rule, no?
Can you repeat your question?
Sir, if some number was associated with I,
I is a number.
sir, imaginary part.
It is a number, na? Complex number.
Yes, sir. For example,
Yes.
4i, if it was 4i, then
Ah.
sir.
If it is 4i, then I will place 4i in the place of z. I is itself a number. Are you getting my point? ये I जो है ये number ही है. I mean, if you are trying to say that z cube minus 4i cube अगर है, then this won't become 0 in the numerator. Z minus 4i. That is what you will get, right? Z tends to I. In this case, you won't get 0 by 0, so you don't have to use L'Hopital rule. So L'Hopital rule can only be used when you get 0 in the numerator as well as 0 in the denominator. Am I clear?
Yes, sir. Yes.
Fine. Next example. F of z is equal to mod of z square at z equal to 0. So I need to check the differentiability of the function f of z is equal to mod of z square at the point 0. Okay. So let's start with this. I'll use another definition just for the practice purpose. But before going to that, let's just see what is mod z square. Mod z square is z into z bar that we have seen earlier. So x plus iy into x minus iy. Z is x plus iy, z bar, the conjugate of it is represented by x minus iy. If you multiply this, you get x square minus ixy plus ixy minus I square y square. This two will get cancelled out. I square is minus 1, so this will become x square plus y square. Okay, so the simplification I'll rub and z into z bar, I'll directly write down x square plus y square. Plus y square. So when I want to check the derivative of a function at z naught, the definition is limit z tends to z naught f of z naught, oh sorry, delta z tends to 0. This has to be delta z tends to 0. F of z naught plus delta z minus f of z naught upon delta z. What is the definition? The definition states that f of z is nothing but mod of z square. So this will be mod of z naught plus delta z square minus mod of z naught square upon delta z. Now we can simplify this just using our basic property. What is the basic property? Mod of z square is nothing but z naught plus delta z into z naught plus delta z bar minus z naught into z naught bar upon delta z. So what do we get? This is equal to limit. You can multiply the two brackets, just the usual multiplication. Z naught plus delta z bar is actually z naught bar plus delta z bar. So I'll just write that step into z naught bar plus delta z bar minus z naught into z naught bar. So we can open the bracket, limit delta z tends to 0, z naught into z naught bar, the first multiplication, plus z naught into delta z bar plus delta z into z naught bar minus z naught into z naught bar. There is one more term, delta z into delta z bar. So those two will get cancelled out. Separate the denominator, limit delta z tends to 0, z naught into delta z bar upon delta z. Plus z naught bar plus this term which I wrote here has to be here like this. So when I separate the denominator, that will be delta z bar. Now the derivative has turned out to be this. And now in this case, I want to check what happens uh, through all the paths. And in that case, what I will do is I'll see what happens if delta z is real. So case 1, if delta z is a real number, okay, it means that as you can see on the complex plane, 0 is here. 0 is this point. So 0 can be reached through x-axis, and 0 I can also come through y-axis. So I'll discuss the two cases if I'm reaching to 0 through x-axis, which means that if delta z is real. So if delta z is real, then delta z and delta z bar, both of them will be same. As when you take the conjugate, it changes the sign of imaginary part. So if delta z is real, both of them will cancel out each other, and f dash of z naught will become this will get cancelled out two times. Sorry, z naught plus z naught bar mm, z naught plus z naught bar. This is what you will get if it is a real. And case number 2, if delta z is imaginary. If delta z is imaginary, then what will happen is if this is I, say for an example, delta z is I. So delta z bar will become minus I. So I and I will get cancelled out. You will get a negative sign over there. So f dash of z naught will become minus of z naught plus z naught bar. This will happen. So f dash of z naught cannot be two different things. Now I will check at 0. So at if z naught is 0, then both of them will become same. Okay. Are you getting my point? If z naught is 0, then both of these will become same. If z naught is not equal to 0, then these two are not going to be same. So that's why what I conclude is f of z is not differentiable anywhere. F of z is not differentiable anywhere except at z equal to 0. Am I clear?
Yes, sir.
If you have any difficulties, you can ask. Or in next lecture, we'll talk about CR equations. No problem? Fine. You can anyway. I'll start with CR equations in the next lecture. Put your name and roll number in the chat box for the attendance purpose.